my great pleasure to introduce Ali Abbara from Imperial. Take it away.
Okay. Good morning, everyone. So my name's Ali Abbara. I'm an endocrinologist, so a hormone doctor. So I mainly deal with reproductive health and infertility. So I'll talk to you a little bit about endocrinology and some of the problems that we face and where mathematical modelling could potentially help, and some of the work that we've done in that area. So infertility is very common. So 1 in 6 couples suffer from infertility, and it's getting more and more common. Obviously, people are delaying when they start to try to conceive, and also a lot of reproductive health conditions are getting more common. Normal menstrual cycle length, even outside of infertility, is now recognised as an important marker of general health. So people with an irregular cycle are more likely to have conditions like type 2 diabetes and cardiovascular disease and so on. So there is an interaction between reproductive health and metabolic health and just general health. So I just thought I'd go over some of the basics of the normal human menstrual cycle. So typically we say the menstrual cycle is 28 days, and actually only a small minority of women actually have a precisely 28-day menstrual cycle. And when the menstrual cycle is irregular, or usually that means longer than typically 35 days, so people have fewer than 1 a month, we say that's irregular menstrual cycles, so oligomenorrhea, and if they have no menstrual cycles at all, we call that amenorrhea, so lack of menstrual cycles. And the reason we sort of worry about that as a condition, usually it implies that ovulation is not happening, so that's a sort of key process in the normal menstrual cycle. In terms of endocrinology, lots of endocrinology has controller hormones that then control another hormone that then feed back onto the controller hormone. So this is the hypothalamus within the brain. There are GnRH neurons which make this hormone GnRH that stimulate another gland in the brain, the pituitary gland, to make luteinizing hormone and follicle stimulating hormone. So these are the key hormones that regulate the menstrual cycle. They then get into the blood and stimulate the ovaries in women or the testes in men, and basically regulate the menstrual cycle. And like I say, they're all subject to feedback loops. So when testosterone goes high, it will then feed back on the hypothalamus and pituitary and so make less of the LH and FSH. There's lots of negative feedback loops, and there's also positive feedback loops. So it's a real complicated system, all aimed at keeping everything in balance. So it's constantly sensing and then reacting to the hormones. And I suppose one of the things to notice also is that GnRH itself is released in pulses, and that's important. So if it's not released in pulses, then you don't get that stimulation of the pituitary gland. So that's also an important feature. So thinking about the normal menstrual cycle, so this is from the ovary. So what happens at the beginning of the cycle, which is called the follicular phase, is that there's a small rise in follicle stimulating hormone, so FSH, follicle stimulating hormone, and that stimulates the follicles. So these are little sacs within the ovary that contain the egg. As the FSH rises, these follicles start to grow. As they start to grow, they make estrogen and another hormone called inhibin. And like I say, these feed back on the hypothalamus and pituitary glands. So as they rise, they feed back and bring the FSH back down. So you get this rise in FSH that then falls. And why that's important is some of the follicles that are larger are less FSH dependent and can continue to grow, whereas the smaller ones need that FSH and so they die off. And so this is the mechanism by which we select out a single dominant follicle. So in humans, only 1 follicle each month, and that's why you don't have twins and triplets, whereas in animal models, sometimes they have multiple follicles develop each month. So this is how you select out a dominant follicle. As that follicle grows, it makes even more estrogen. And what's interesting is, at low levels, estrogen causes negative feedback. At high levels, it causes positive feedback on the hypothalamus and pituitary. So that estrogen, when it gets to high levels, then induces the LH surge. So that's in midway through the cycle, you get this rise in LH, and that's important for ovulation, so for inducing release of the egg from the follicle. So that's ovulation, and that's obviously important for fertility. Now the rest of the follicle that's released
Can I
the
ask
egg.
a question? I thought that the GnRH also shows that surge as well. So it's upstream of LH, isn't it?
Yeah, so basically GnRH happens in the brain, and we can't really measure GnRH. So you would have to be able to measure it within the hypothalamus. So we use LH as essentially a surrogate for GnRH. So there is data showing it's a one-to-one relationship that LH represents GnRH. You can, I don't want to get into complexity, but you can get an LH surge without the GnRH surge. So it is possible to bypass that. But yes, generally it's thought to be through the GnRH. Yeah. So the remainder of the follicle becomes the corpus luteum. So corpus luteum, yellow body, because I think that's how it looked on histology. And that's the one that produces progesterone and estradiol. And that's important for preparing the endometrium for a pregnancy, should it happen. So, and usually that's how we assess whether ovulation has happened. We do a progesterone level halfway, so day 21, halfway through the second half of the cycle, the luteal phase, to see if ovulation has happened, essentially. But obviously that's not particularly accurate. Not everybody is as regular as that. If a pregnancy does happen, that will then make beta-HCG and will maintain the corpus luteum because it's sensitive to beta-HCG. If it doesn't happen, then the progesterone will start to fall, and then that induces the next cycle. So that's basically how the sort of menstrual cycle works. But so one of the things that we do as clinicians is try and figure out whether the person has a normal cycle length, because like I say, that usually implies that they're ovulating regularly and they're fertile. But it's actually not perfect. If you look at the different guidelines, they have different thresholds for when you have abnormal cycle length. So some say 36, some say 38, some say 35, some say 45 for amenorrhea, for example. And not only that, about a quarter of women with regular menstrual cycles also are not ovulating on that cycle as well. So we typically assume that they're ovulating, but it's also not always true that they are. So this is data from the Flow app. So a lot of people now are recording their menstrual cycles on all these digital apps. And you can see that actually only 16% of women actually had a 28-day cycle. So we typically say that for most people who have a 28, it's actually a sort of minority. Obviously, variations around it. So most people are in that region, but it's not as precise as we like to make out. And that obviously has implications for when we measure hormones and how we interpret the hormones, because obviously they're going to be different for different times in the cycle. And in terms of what determines it, it's the first half, the follicular phase, that seems to have the biggest impact on the length of the total menstrual cycle. So the luteal phase, once it happens, is pretty stable, but the follicular phase, the first half, is particularly important. And things that impact on menstrual cycle length, so age is one. So in the run-up to menopause, obviously menopause is when you lose menstrual cycles and they stop completely. But in the run-up to menopause, often cycle length shortens. And that's possibly due to a hormone called AMH being lower with higher age. And likewise with BMI. So at very low BMIs, there's a slightly longer cycle length, and as well with obesity. So I'll come on to a condition shortly that might explain that. Okay, so like I say, the main reason that we're interested in cycle lengths is that it has an implication about ovulation. So if someone has infertility, one of the first things we're trying to assess is, are they ovulating regularly? If they're not, we might try and restore ovulation. If they are, obviously we're looking to sort of other reasons. And it's not particularly precise. Usually, there's not huge amounts of data either, but usually the sort of progesterone level, sort of more than 15.9, is used as a sort of marker to confirm ovulation. But it's not always done because you have to time it regularly as well. So it's often assumed based on cycle length. Okay, so what we have in the menstrual cycle is a series of processes. They're sequential, so one follows on from the other. So follicular development will follow on to estrogen going up and inducing that LH surge to induce ovulation, which will then induce the corpus luteum, which will then induce, so they're sequential. They're all subject to feedback loops, and it's basically quite a good situation for mathematical modelling to try and make sense of it. So this is Dr. Olga Nev at Exeter. So I'm sure she would have been here. I think she's had a baby recently. So, but she's been working on trying to map, sort of model the menstrual cycle. So this is a complicated diagram that she's sort of put together. And this is a very simplistic model, the sort of pilot type of model, but it sort of replicates a lot of the hormonal features that we see in the natural menstrual cycle. And like I say, the reason you'd want to do it is to try and exclude anovulation. So the two commonest causes of anovulation, the first one is polycystic ovary syndrome. And that one, you also have 2 of 3 features. So one is an irregular cycle, another is high androgen, so things like excess hair growth or acne or high testosterone in the blood. And then you have a specific feature on ultrasound as well that suggests polycystic ovarian morphology. The second commonest cause is hypothalamic amenorrhea. So this is a condition with low body weight, where essentially there's not enough energy for fertility, and the whole reproductive axis shuts down from top to bottom. So you have low GnRH, low LH, and so on, and so therefore the whole axis shuts down. So those are the 2 commonest causes. Polycystic ovary syndrome is typically a condition of high GnRH pulsatility, and so therefore you get high LH levels, whereas hypothalamic amenorrhea, you get the opposite, you get low LH levels. And so this is some of our data on the left is, if you have very high LH levels, you're more likely to have anovulation, and also if you have low LH levels, you're more likely to have anovulation. And what was quite nice is the very small pilot model that she's produced so far. If you increase the LH, again, it extends the duration of the cycle length, and likewise if you reduce the LH. So replicating what we actually see in practice, predicting that you would get anovulation in those situations, which is quite nice. But in practice, differentiating hypothalamic amenorrhea and PCOS is actually quite challenging. So we did this review looking at some of the features that you could look at. But one of the ways that they do differ is, like I say, with respect to hypothalamic function. So in PCOS, it's overactive, and in hypothalamic amenorrhea, it's underactive. And we do some work with a hormone called kisspeptin that works specifically in the hypothalamus, so it can tell us about hypothalamic function. And so this is a study that we're working on at the moment, and essentially we give a bolus of kisspeptin at time 0, and then you can see the hormonal response, and you can see that in hypothalamic amenorrhea they have an increased response, whereas in PCOS they have a reduced response. So again, reflecting this hypothalamic activity. So a little bit more about hypothalamic amenorrhea. So like I say, it's low energy, and then that leads to lack of periods, low estrogen. Obviously that can have a damaging effect on bones and on fertility. And it's a condition of reduced GnRH pulsatility. So this is where they sort of found this study. So essentially what they got, healthy, regularly cycling women, and the numbers are basically the amount of calories per day for lean body mass. So they gradually restricted their calories, and essentially once they got to less than 30 kilocalories per kilo of lean body mass, you can see that the number of pulses started to reduce, so you get a reduction in the GnRH pulse frequency. And so basically that's where that's come from, as a sort of minimum energy that you need for fertility.
Sorry?
Yes?
But the pulses get stronger?
That is true, yeah. So they do. There is this, so the fewer pulses, sometimes they can be larger. In our women with HA, which I'll show you one, when it gets really severe, they just go, they're lost completely. So then they go completely flat. We don't often, so sometimes we see this sort of increase in size, but not always. But it is recognised that you do get well spotted. A lot of endocrinologists haven't spotted that. Yeah.
While we're at it, can you look at kisspeptin as well and see what's happening to kisspeptin during this?
Well, I suppose that's what we did in that previous study in terms of response to kisspeptin. Kisspeptin in the blood is quite low levels. So again, it's a hypothalamic hormone. So outside of pregnancy, you don't really have high levels of kisspeptin. So we've done some work on pregnancy, and then it's very easy to measure. Outside of pregnancy, it's just very hard to measure at low levels. There are some data with ELISAs, but we're not sure how reliable they are. So there are some that show slightly higher level.
Animal models, for example, to during pregnancy to see how that affects it with high calorie.
Interesting. Yeah. So if you have very high calorie wise.
Yeah, in terms of comparing these two conditions.
Yeah, so there is data in terms of, you mean like expression in the hypothalamus? Mm-hmm. So there is data both in high calorie and low calorie states that you have reduced kisspeptin expression, and sometimes that leads to upregulation of the receptor. And so that's why we think in hypothalamic amenorrhea, when you give exogenous kisspeptin, you get an increased response. That doesn't seem to happen in obesity, at least not in male obesity, so male mice had a reduction in the receptor. So we are doing some work.
You're talking about kisspeptin receptor?
That's right.
In the genealogy unit?
That's right.
Okay.
That's right,
yeah.
Okay, but I suppose what I was hinting at is the pulsatility can be affected in these conditions. And PCOS, so the pulsatility tells you about the endogenous activity of the hypothalamic GnRH pulse generator. So that's typically increased in PCOS and reduced in HA, so in hypothalamic amenorrhea. And so one of the things that you'd quite like to do is be able to objectively assess pulsatility. So for example, in the natural cycle, you get a pulse in the follicular phase every 90 to 120 minutes. Whereas in the luteal phase, it slows. And so that tells you about the activity of the GnRH pulse generator in those situations. And this is the data I think I was referring to. So on the bottom left is a sort of roughly a normalish pulse, LH pulsatility. On the top left is what we see in women with hypothalamic amenorrhea. So often flat, you can occasionally get the odd pulse, but generally very little pulsatility. So low pulsatility. And like I say, it could be due to a lack of kisspeptin. So in this study, we were giving kisspeptin as an infusion under the skin. And what you can see is as soon as you do that, you can start to restore LH pulsatility. And this is 11 days after stopping the infusion. So it carried on for 8 days. And then a month later, it sort of goes back to how it was, so completely flat.
Sorry, this is fascinating. So with the kisspeptin, is it infused in a pulsatile manner or at a constant level?
No, it's a really good question. So it's not. So yeah, and the reason, so I suppose what you're asking is a really good question, is how can you give something continuously to then induce pulsatile? So that I don't think we know the answer for sure. GnRH neurons have an inherent pulsatility, just like cardiac myocytes have an inherent pulsatility as well. So there is this idea that even though it's flat on the top left, it's possible that there are micropulses that we can't see, and all you're doing is amplifying the endogenous pulsatility. But that's really more of a theory rather than, as in it's hard to prove that. Okay, so assessment of pulsatility would be useful for assessing activity of the hypothalamus. And I think we can all agree that there's clearly a pulse there, But is this a pulse? This little blip? Probably a pulse. It looks the right shape. You get this sort of rapid upstroke, and downstroke is a bit longer. And that's probably because obviously the GnRH is sort of quite rapid and short, and then you get the sort of half-life of the LH as it sort of falls. But it's quite hard to say exactly how many pulses are there. It's not easy to say exactly how many pulses there are. So this is Professor Johannes Veldhuis. I think he's retired now, but he was at the Mayo Clinic. And essentially one of his major things was to assess pulsatilities. So people would send him data from all around the world, including us. And so he would basically say how many pulses there are in this, and that became the sort of gold standard method. I think he used a sort of deconvolution analysis that he developed. But I think he's retired now, so I don't know how anyone would do it now. And thankfully, Margaritis, Voliotis, and Crassi, who I'm sure you all know, developed a sort of Bayesian formula for doing the same thing. And essentially, so it's called hormone based, so it's open access, so anybody can now access that and assess pulsatility. And it correlated very well with the sort of gold standard method that was used for many years. This is probably above me, but basically I think they essentially tried to figure out the probability that the GnRH neuron was firing. And I think that's how I understand hypothalamic signal from 0 to 1. And I think more than 0.5 is like it's more likely to have fired than not. That's my simplistic understanding of that. Essentially, yeah, so they basically looked at different conditions. So this is our sort of clinical data, women after the menopause in HA, in men, healthy, and men and women. Okay, so that's hormone bays. I'm going to move on to infertility and IVF treatment as well. So we did some sort of research in that setting. So just the very basics of IVF treatment. Essentially, rather than the natural cycle, you get a small rise in FSH. In IVF, they use a much higher dose, and you get lots of follicles develop. They then collect the eggs directly from the ovary. They then introduce them to sperm in vitro, and that will hopefully, they will then fertilize them, and there's basically two ways of fertilizing. You just leave all of the sperm with the egg in a dish, and that's called IVF, or you can take a single sperm and inject it into the egg. That's called ICSI, and that's usually used if there's a problem with sperm, so if there's only very few sperm or something like that. You then hopefully find embryos, and then you pick out an embryo and put it back into the endometrium to try and resolve the pregnancy. And again, this is a sort of multi-step complex process with lots of dosages and timings that differ from person to person that we try to personalize. Basically, the number of eggs that you get out is important, especially at the lower end. So the more eggs that you get out, especially less than 15, has a dramatic impact on your chance of pregnancy. But having said that, this is in the UK, about 7% of protocols don't actually, 7% of women don't have any eggs retrieved and 12% no embryos retrieved. So there's definitely room for improvement. Some of that is biological, but some of that is we can improve things. So I'm just going to go through the protocol in a little bit more detail. So we give them higher doses of FSH, and you hopefully will then grow lots of follicles. But you wouldn't be able to collect them at this stage because the eggs are still immature. The next thing that you want to do is stop ovulation happening too soon. Because they collect the eggs directly from the ovary, if they've already ovulated, there'll be nothing there to collect. So the second thing that we do is we give something to prevent that LH surge, the ovulatory LH surge. And that means that ovulation won't happen, and then you can give time for the follicles to grow to the right size. This is the bit I was thinking about before, but we can't collect them at this stage because they're still immature. So we've stopped ovulation happening, but that ovulation is important, that LH exposure. And what it does is it makes the egg go from a diploid to a haploid. So initially it will have 46 chromosomes, but during that maturation process, it will lose half of its chromosomes, and then it's ready to be fertilized with the other half from a sperm. So that's called maturation, and that happens in response to LH. So initially we prevent it, and then we give the LH once the follicles are the right size. And usually that's done with HCG. So HCG is a pregnancy hormone, but it acts on LH receptors, and so it's like giving LH. The problem with it is very long acting, and therefore you can overstimulate the ovaries. So we've already stimulated the ovaries very strongly with the FSH. We then give another really strong stimulation, and that can overdo it and cause this ovarian hyperstimulation syndrome. So essentially, the ovaries release lots of harmful chemicals, you get leakage of fluid in all the wrong places, and that can be quite a dangerous condition. You can go to ITU and various things. So you can see it's a complex multi-stage process, and artificial intelligence is really blooming in the area of IVF treatment. So there's lots of areas where you could potentially use artificial intelligence. This is one of our reviews where we sort of summarize some of them, but there's an explosion in the field. But this is about some of our work. So one of the things that you want to do is decide when do you give that trigger of LH exposure. So you want the follicles to be large enough, but not too large, but not too small. But the way they currently do it is you give the FSH, you monitor every other day or so with an ultrasound, and once the top 2 or 3 follicles reach 17 or 18, depends on which unit you go to, they then say, okay, we're ready to give the trigger. So that's the HCG or GnRH agonist, for example. And so the idea is the top 2 or 3 represent the rest of the follicles. So they all, and that's probably true if they all grow together, like in this scenario. But let's imagine the top 2 or 3 are disparate from the others, and then in that situation, it's a bit misleading to just use the top 2 or 3 follicles. And so this is the question that we sort of sought to answer, is which are the follicle sizes that are important to give you an egg? So this is on the day of collection. So you give the trigger, and then a couple of days later, you collect the eggs. And this is looking at the different sizes of follicles on the day of collection. And you can see that if they're very small, they're not going to give you an egg. And if they're very large, sometimes they're slightly less likely to give you an egg. It's not so obvious on this one. But sometimes they can be post-mature as well. So there's this sort of intermediate size that's probably important, but it's not really been defined. It's been defined on the day of collection, but that's too late because you make the decision 2 days later. So you have this problem of follicle sizes on the day of trigger, and then number of eggs collected 2 days later, and then we're trying to see which of the follicle sizes that are most likely to have resulted in those eggs. And the reason we got interested is that kisspeptin, as I mentioned already, is also thought to be the natural inductor of ovulation. So we did this study where we used kisspeptin instead of the HCG. So HCG is the sort of most usual trigger, but it's most likely to give you the side effects. Whereas kisspeptin is slightly shorter acting, and essentially what we see is that you get much fewer signs and symptoms of that OHSS if you use kisspeptin compared to HCG. Whilst we're doing those studies, obviously we needed to assess how effective is the kisspeptin as a trigger. So in order to do that, you need to understand what is the optimal follicle size that should give you an egg if you gave it an effective trigger. So for example, if you have 9 follicles in that optimal size and you get 9 eggs out, then the trigger has done its job. Whereas if you have 9 follicles and you get 3 eggs out, then it hasn't done its job. You've got fewer eggs than you should have done if you'd given effective triggering. Conversely, if you had 3 follicles in that range and only 3 eggs, then it actually has done its job. And this is not something that's particularly well recognized in the IVF world. They just look at the number of eggs and then they'll say overall how well did the trigger do. But it depends on what it had to act on. So the follicles will depend on the FSH rather than the trigger, if that makes sense.
So the number of follicles versus the number of oocytes, I mean, is that an indication of like, you know, downstream if there's some other issues in terms of fertility, or just explaining the effect of the inducer?
Yeah, so I mean, so let's say in this situation, there's lots of follicles on the day of trigger.
Yeah.
Let's say you got 9 eggs out. So this, as we saw, some of the smaller ones, you wouldn't expect to give you eggs, even if you give them adequate triggering.
Yeah.
So the idea is, can you identify which ones should give you eggs? And therefore you can assess the efficacy of the trigger itself. So it's basically separating out that process. So for example, when they talk about poor ovarian response, they won't separate out whether the response was poor because they didn't respond to FSH, or as poor because they responded to FSH beautifully, but they only got 3 eggs out. So it's basically trying to be precise in understanding which bit does which bit. So the trigger is only responsible for getting it from the follicles to the eggs, but they sort of mix and match them. So they just talk about poor ovarian response as 2 processes, but then they only really think about the 1 process.
I get this, I understand what you're trying to say, but what I'm trying to say, or my question is what, like, you know, for later on using these eggs to be fertilized, etc. So if the efficiency is less with the trigger, does that have any side effects downstream?
Oh yeah. So if you have 9 eggs and you only get 3 eggs, then obviously IVF is a really profligate process. So if you start off with 9 eggs, not all of those 9 will be mature. So maybe about 8 or 7 will be mature. Not all of them will then fertilize, so to form a zygote. So maybe you might lose another 2. Then not all of them will become blastocysts, so on day 5 and grow into a nice embryo. Not all of those will be high quality. So you might start off with 9, but you might end up with 2 blastocysts. So you want to start, so that's why I was showing you that graph about, you want to get at least 15 really, on average. So you want to start off with lots, so that by the end, you've got at least 2 or 3 good blastocysts to be able to put back. So if you've lost it in that process, so I'll show you actually some data on that. Okay, so that was the question, is in which follicles are too big and which follicles are too small. So there's a sort of Goldilocks, but it's not well defined. And it's important to define that is because we make the decision at this point, not in 2 days later. Once you're doing the collection, it's too late, essentially. I won't go through this, but essentially there's a sort of, in healthcare, there's a sort of idea to try and use explainable models as much as possible. And we basically use random forests. So we were working, this was a few years ago, so when we first asked this question, this is with Prof. Kelsey at the University of St Andrews. And essentially, we were sort of looking at a data set from Vietnam, from a randomized controlled trial, and he essentially identifies the follicles with the highest probability of giving eggs and mature eggs. And then more recently, we've done this on a much larger scale. So we now have data from 20,000 cycles from across the UK and Poland. Essentially, we're sort of able to give a probability of each follicle size giving you an egg. So you can see that the ones in the middle were the ones that are most likely to give you an egg. So it doesn't mean the ones slightly outside that can't, it's just that their chances are lower. So this is useful. We also then had a look at downstream things. So mature eggs, again, you can identify the sizes that are most important for that. And then high quality blastocysts seem to be most in the middle. And then they sort of validated it with another form, so SHAP analysis, and again it seemed to match quite well with the random forest. Not everybody has a scan on the day of trigger, so this is the sort of distribution on the day of trigger, but we also looked the day before and then the day before that, and there was a nice stepwise reduction, which is sort of helpful that it's not just spitting out random numbers, that it is actually sort of following sort of logical distribution as you'd expect. We also had a look at different protocols, so the different ways of preventing anovulation to see if that affected the sizes, and also different age groups. So there's this idea that in older women you're more likely to have premature luteinization sooner, so you might want to trigger at slightly smaller sizes, for example. And essentially what we showed, so on the left is the standard current method. So if you meet the criteria for either 2 or 3 follicles being 17 or 18, so 2 or 3 of the largest follicles. And then on the right is what happens if you try and maximize the number of follicles within that optimal range. So the higher the proportion of follicles within that range that we identified, the greater the oocyte yield, the greater the number of eggs that you were able to then get out. And not only that, the higher the percentage within that range, the better the pregnancy rates as well, the live birth rate. So you could improve the live birth rate by maximizing the proportion within that. Another thing we noticed is that if you just looked at the average size, if the average size of the follicles was larger, that had a negative impact on the live birth rate. So why might that be? So this is looking at the number of follicles that is above the highest part of the optimal range. So these are a number of large follicles, and they start to make progesterone. So the more of those that you have, the more progesterone that you make, and you're not really supposed to make progesterone at that stage of the cycle. And what it does is it starts to mature the endometrium, and basically it becomes out of sync with the embryo when you put it back. And so basically the higher the progesterone, the live birth rate starts to drop. So you can see that in blue. So this is recognized in terms of they measure progesterone towards the end of the cycle and might freeze embryos if the progesterone starts to rise. But here we sort of link it to the follicles being pushed too far, essentially. So if you have too large follicle sizes, that seems to do that. So like I say, the reason to do it initially was so that we can grade the efficacy of oocyte maturation, and it means that you get different hormonal responses to the trigger. So we give HCG or GnRH agonists, and the LH goes up different amounts, and you can relate the rise in the LH to the efficacy of the trigger. So if you have a very low LH, and there are endocrine reasons why that happens, the response to a GnRH agonist will be lower, and so therefore you get ineffective triggering. But we're not very good currently at measuring that, and that's because we don't really assess which follicles should give you an egg. So it enables us to basically assess that in more detail. So how important is it to get it right from the beginning? So the other reason is it gives you a target for your FSH stimulation. And we did do some work looking at dosages versus the average follicle size after 5 days, and there's a relationship there. And once the follicles start to grow, they tend to grow in a predictable fashion. So this is day 5 versus day 7 of stimulation, day 7 versus day 9. So once they start to grow, they then grow pretty predictably. But let's say there's a situation where you started too low a dose of FSH. You then do the first scan 5 days later. You get some growth, but some of the most sensitive follicles might grow, but most of them won't. You might then increase the dose, and then you might get growth of another group of follicles that are slightly less sensitive. And essentially what happens by the end of stimulation is you've increased the spread of the different follicles, and then less of the follicles are in that optimal range that we identified. And essentially what we show here is that if you have to adjust the dose, you get less of your follicles within that optimal range, and then you get fewer eggs out than you should have done, because they're not in the optimal range for the trigger. So we've done some work recently just looking at, can we predict follicle growth during that stimulation phase? So there's some really rudimentary data that exists in the literature where they basically calculate the average follicle size on one day, calculate the average follicle size on another day, and just do the difference. And so you can get a difference in the mean follicle size. But what we did here was look at each individual follicle and then calculate the growth rate for each follicle to assess basically whether different sizes on different days of stimulation grew differently, and whether so there's this idea that towards the end of stimulation they start to grow faster. And so basically what it means is from a very early scan, you can predict the follicle sizes on the end of stimulation. And you can, so basically 22% perfectly, and then the sort of vast majority within a millimeter's difference at the end of stimulation. Okay, so to conclude, I've hopefully shown you some examples where potentially mathematical modelling quite suits a lot of endocrine and fertility treatments. There's lots of complex feedback loops and sequential processes that I think would suit sort of input from mathematical modellers. Happy to take any questions.
We've got time for a couple of questions. Yeah, thanks very much. Very interesting talk. What's the adoption like for this kind of work? I mean, it's really interesting, and it seems like you get really clear-cut results in terms of, follicle size and that. So, but how willing are clinicians to adopt these strategies?
Yeah, so IVF is a weird world. So half of the cycles, or more than half of the cycles, are in the private sector. So they're very ready adopters to new technology. And that's sometimes good, sometimes quite bad. So there's loads of examples where they've adopted things really, really quickly. So there was, I'll give you an example, there's something called endometrial scratch. So what they found was when they were doing a biopsy, people were more likely to get pregnant on their next cycle. And so they thought, well, let's start doing, not biopsies, let's just start scratching the endometrium and offering it as a service. So that then became widespread, and so you offer it for a few £100 sometimes to scratch the endometrium before your cycle to try and improve the chance of pregnancy. And if you're investing, let's say you're a patient and you're investing, say, 10, 12 grand into a cycle, and someone says, well, there's this thing, it's £200, it probably won't, it might not make a difference, but it might help. It's almost crazy not to spend 200 to make your 12,000 go further. And so even if they're very honest about the lack of data in certain fields, they will offer it, and patients sometimes will ask for it. So they'll say, I've heard about this scratch, why aren't you offering it to me? So it's both ways, but then they do these like massive trials and show that it doesn't really do anything. And that's not the only thing. There's like a million such things in IVF, so they're called add-ons. And you can have a series of things that you can add into your treatment that might help, but probably won't, and the evidence is very weak. So if the evidence is weak, if it was strong, it would be part of routine practice, but oftentimes it's not. And so they're optional add-ons. And I think there's probably the same with this. So there's an AI, for example, for selecting embryos. There's a special incubator that you can use for growing the embryos and not disturbing them, for example. But so far, there's a whole move, there's a lot of startups. So the whole move to offer these, sell these, get them into clinics without necessarily proving they make any difference. So, for example, so there's been very few randomized control trials of AI models and what impact they have on clinical outcomes, and the one that's been done was negative. So they were trying to show non-inferiority, so not even superiority, they were trying to show non-inferiority to an embryologist doing it, and they weren't able to show that. It's not easy, so to do a randomized control trial takes 5 years, and so the model might well have changed hugely between the beginning and the end of that trial. So there's a lot of particular issues in that field, especially if you're trying to get a model to learn and change constantly. But I do think it's important to prove these things before they're adopted, especially if we're selling them, because that cost is often passed on to the patients as well.
Nice. And just a second question, quick question. One of the groups, you were talking about the length of the menstrual cycle was like greater than 45 days. What? That seems quite large, no?
Yeah, so essentially they've not cycling at all. So that's basically amenorrhea, means lack of menstrual cycles. But for example, women with functional hypothalamic amenorrhea, it's due to low body weight. Every now and then they might have the odd cycle. So you have to put a definition of where they're still amenorrheic in essence.
I wanted to ask about hormone-based specifically.
Yeah, sure.
Are you using that in your practice?
Well, I mean, pulsatility, to do a pulsatility, we bring patients in and measure blood tests every 10 minutes for 8 hours to get enough of a time frame and enough points to see pulses. So it's not used in clinical practice. So we do it as part of research.
Yeah.
But again, it's not cheap to do that. So if you're doing 50 blood samples, they're maybe £20 each. And in the NHS, you'd need a person, you'd need all sorts of things.
Yeah.
You would need to prove the cost is worth it to be able to do those sort of tests.
Yeah. It's one of the topics that we've been exploring over the last few days are barriers to take.
Yeah, so I mean, I haven't brought it up, but we're looking at sort of relatively, not I was going to say non-invasive, but relatively non-invasive methods where you could measure LH, for example, for longer periods.
Yeah.
So if that existed, then you could it might be easier to roll out on a sort of larger scale.
But so you mentioned there was a professor somewhere that you used to send data to.
Yes.
So what are you doing now?
So hormone-based is equivalent, so it gives you the same results essentially.
But you said you're not putting your data through hormone-based.
Oh no, we are.
Oh,
we
you are?
Yeah,
Okay,
yeah.
cool.
So we work with Margarita and Chrissy, we helped develop that. So,
but you're using that for research rather than clinical practice.
Exactly, yes. Yeah. As in pulsatility generally is just not used in clinical practice.
Yeah, I understand. Yeah. One last question, I think.
Okay. All right. So I'm gonna mention some of the bits and pieces of what I know about the system, and show you where I am confused about, and maybe you can give me your take on this and your hypothesis of what's going on. I was intrigued by that experiment where you're infusing kisspeptin, and you're saying that, you're suggesting that there's this amplification of these micropulses within the LH. So if we go upstream a little bit, I mean, we know that GnRH is pulsatile. And you need to have that pulsatility in order to trigger fertility. At least that's my understanding. So, I mean, some experiments showed that if you apply constant GnRH, you lose fertility. If you change even the frequency of the pulsatility, might be also affected negatively. So let's go even more upstream. You have the kisspeptin, which I don't know if anyone knows if it's pulsatile or not. We know that calcium signals are kind of 8 minutes calcium oscillations that you see in these neurons. One could argue maybe it's an 8-minute pulsatility in kisspeptin. One last point that I'd like to say. So, if you look at cultures, for olfactory black coat cultures, the GnRH there is pulsatile, yet there's no kisspeptin. So how do you reconcile all of this if there is a way to reconcile all of this?
Yes. So actually, yeah, that's interesting about the olfactory one. So that's something that we've sort of been looking into recently with intranasal kisspeptin, stimulating those directly. In terms of the GnRH neurons, so upstream of those is kisspeptin neurons. Those neurons are now called candy neurons, so kisspeptin, neurokinin B, and dynorphin. And the neurokinin B stimulates the activity of those neurons, and the dynorphin stops the activity. And the receptors are on the same neurons. So it's like the neurokinin. So this is the model that's often put forward. It's more proven in animal models, to be honest. But the neurokinin B starts the pulse, and the dynorphin stops the pulse is the idea. And then the output of those neurons is kisspeptin. And it's been shown that kisspeptin is pulsatile so they've done microdialysis from the hypothalamus in monkeys, and they've shown the kisspeptin is pulsatile. And the output is kisspeptin, essentially just kisspeptin onto the GnRH neuron in pulses. And if you have conditions where you lack kisspeptin, then the system shuts down. So there are patients, and that's how kisspeptin was originally identified, is there are patients with genetic abnormalities that means that they don't have the kisspeptin receptor, and then the whole system shuts down. So they have low GnRH, low everything. Actually, they didn't have low GnRH. They looked so at that point, they didn't know why the system had shut down, and the GnRH was still there.
Oh.
But it wasn't, the LH was low, and etc.
I see.
Yeah, so there was no stimulus for the GnRH to continue. Okay. So it has inherent pulsatility, but I think it might be to do, again, like you said, about how much is actually released. So without the kisspeptin stimuli, you don't get, you get a flat line of the LH.
Is it possible
can we leave the rest of the discussion for a break? Thank you. Let's thank Ali again.
No worries.